Hello guys, hello and welcome to this presentation that is part of the event Spain Global Azure. I will start by thanking our sponsors and the sponsors of this event, Avandi, Bravant, Clever Task, Encamina, Entity Data, Elitia, Insight, Intelequia, Cable K, MyCloud Door, the company that I am really proud to be part of. Um, Nuncis, Plain Concepts, Prodware, and of course Microsoft. Thank you for making this event possible, and thanks for this experience and the opportunity. Moving on, my name is Mohammed Aziz Khalfallah. I am a data scientist and business analyst working currently with my cloud door as a cloud consultant. Today I will be presenting and we will be talking about recommendation systems, and most importantly we will touch on the concepts of the collaborative and content-based filtering systems. It will be like this. We will start by an introduction, basically a description on what are the recommendation systems, their benefits, and the different types. And then we will be talking and diving deeper on the concepts of the two most important filtering systems, that are collaborative filtering and the content-based filtering. And ultimately, we will see a real project example we did for a client. Starting with an introduction. So, what is a recommender system? A recommender system refers to a system that is capable of predicting the future preferences of a set of items for a user. One key reason why we need a recommender system in our day and age is that people have too much options. We have access to too many options, too many items, and too many choices. Like in the past, people used to shop in a physical store, in which the items available are limited, like limited by the actual size of the book, the store itself. But now, thanks to the internet, we have access to an abundant amount of items and data and choices and information. The problem is people now have a big problem or a hard time selecting or actually um, finding the items they actually want to see or want to consume. This is where the recommendation systems come in. So the benefits, apart from recommending items and solving the problem of the choices, obviously the recommendation system narrowed down the selection pool and enhanced the consumer experience. But this naturally, by doing so, naturally would add more value in the following ways, like better customer retention. For example, as customers get to explore content that interests them, that they are actually interested in, they are more likely to explore the collection that you have or that you are providing, than go, for example, and look for your competitors. And enhancing their engagement. So as we start recommending relevant recommendations, it becomes easier to target them with fresh content. Like, it's easier to target our users with fresh new content. And of course, building loyalty. And this is because customers appreciate businesses that value their time, and through relevant recommendations, by providing them with the right recommendations, we save them time. So, and with that, by retaining customer, enhancing their engagement and their experience, gaining loyal base customers, we automatically increase our sales. And the good thing with scalability, with the recommendation system, that they are scalable. So no matter how many users, how many items, how many data we have, it's really scalable. Like we can we can after all this is the purpose of the recommendation system. The more items we have and the more users we have, we narrow down the selection to specific recommendations. So it's really scalable. It works with a lot of data, like an enormous amounts of data. Like for example, Amazon have billions of users and millions or billions of items, and they are recommending items successfully. And we can do the same thing with with the little items as well. So we can up the scale and we can narrow the scale. It doesn't matter. So it's really flexible. It's really scalable. And recycling content is basically by monitoring the behavior of the client, of the user. We can detect some interests of some users or detect some niche categories and recommend the content of this niche to those few users that may have interest in. This works basically that there is items or categories that some users doesn't even know that they exist because they're not that popular. But by observing and monitoring the behavior of some of the users, we can detect the interest and in these type of items or in these categories, and we can recommend them. This is basically recycling content. So the content that no one is consuming, by using the recommendation systems, we can recommend it to the user, and that way can be consumed. So I hope this makes sense. So we will see the different types of recommender systems. There are many. So what are the types of recommender system and which are the most important? Let's focus on the most important ones. So there are a lot of different types, like for example the collaborative filtering and the content-based filtering that we will be touching with more details later. The demographic based filtering, which is really simpler. I think that this is the most simple recommendation system there is. Basically it takes the most popular item and recommend it to almost everybody. So it's really basic and it's not that effective. We have the utility-based filtering, knowledge-based filtering, and hybrid filtering, which is ultimately taking different types of filtering and combine their results together to get the best of both worlds. And who knows? Maybe there is more. Maybe there is more filtering types. So even though the artificial intelligence is fairly new concept in comparison with other domains, I mean the mathematicians and data scientists have been really busy. So the, I'm sure there will be more types of ways or more types of algorithm than those. But typically, these are the commonly used algorithms, and traditionally the two basic methods to construct a recommender system. So knowing these two is really sufficient. So we have the content-based filtering, as we said, and the collaborative filtering. These two are the bread and butter of recommendation systems. And the first one analyzes the nature of each item. So, for instance, recommending poets to a user by performing a natural language processing on the content of each poet, like the item itself. And the collaborative filtering, on the other hand, does not require any information about the item or the users themselves. It recommends items based on users' past behavior, like we said previously. And we will elaborate more on these two concepts in the next slides. First, we will start by the collaborative filtering system. As we mentioned above, the collaborative filtering is a mean of recommendations based on user past behavior, and there are two different categories. First, the user based, This measures the similarity between target users and other users. The target user are the users that we will be recommending items to, okay? And the item based, which almost does the same but with the items. So measure the similarity between the items that target user rates interacts with another item. So we will take the items that the user liked, and we will do a similarity analysis of the items to find items more similar to the items that the user liked, and we recommend those items at the end. I hope that makes sense. So the key idea behind collaborative filtering is the similarity. Is that similar users share most probably share the same interest, and the similar items are liked by a user. So to explain it more logically, we have this graph and these users. So imagine that we want to recommend a movie to a friend. So let's say his name is Stanley. We could assume that similar people will have similar taste. So suppose that me and my friend Stanley have seen the same movies, and we rated them almost identically. Like we share the same taste. But Stanley hasn't seen, let's say, the Avengers. It's a very popular movie, and I did. If I love that movie, it is probably logical that he will too, right? So the user-based collaborative filtering uses that logic and recommends items by finding similar users to the active user, like to whom we are trying to recommend a movie to. And this is explained by this table here. So let's take the target user E, and we will try to determine if he will like this item, which is I think a TV, will like it or not. So what we will do is try to find the most similar user to the user E, which in our case will be probably user C, because the two users liked pictures, the two users liked books, and lucky for us, we have a feedback of the TV from the user C. And apparently user C didn't like the TV, so based on that logic, the recommendation system, the collaborative filtering, will assume that user E wouldn't like it either, so it wouldn't recommend it to him. Make sense? Okay, so now the question is, how do we measure the similarity? There are two options: a Pearson correlation and a cosine similarity. Let's illustrate it with a concrete example. So this table, since user A and F do not share any movie ratings in common with user E, their similarities with user E are not defined in Pearson correlation. Therefore, we only need to consider user B, C, and D. So based on Pearson correlation, we can compute the following similarities, which are in the last column. And based on the results, we can see that the user C is the one with the highest similarity score, and the user D is the one with the lowest similarity score. So from that table, we can see that D is very different. This is the type of conclusion this is the type of conclusion we can get from the table. So the user D is very different from user E, as the Pearson correlation between them is negative. They are basically the opposite of each other. And based on that logic, let's take, for example, the user D rated Sherlock a 1, so he didn't like it. Based on that logic, since the two users are practically the opposite, what will the recommender system will do is say, oh, so the user D didn't like it, so most probably user E will, because they have different tastes. So it doesn't work only with the similar taste, it takes the different taste in account as well, and into consideration as well. So yeah. And although computing user based filtering system is very simple, it suffers from several problems. One main issue is that users' preference can change over time. So one day you will like an item, then the next day you will like another. So one day you will have a taste, that the second day you will have another. So when the tendencies and fashions and all. So things change, preferences change. So pre-computing the metrics may lead to bad performance. So to tackle this problem, we can apply the item-based filtering. And let's explain it the same way. So back to our friend Stanley. Instead of focusing on his friends and me, for example, and the similarity between them, we could focus on what items from all the options are more similar to what we know he enjoys. Let's focus on the items similar that similar to the items he enjoys. Like the comparison is with Stanley himself. We don't use other users or other similar users to judge and to recommend items to Stanley. So instead of measuring the similarity between users, the item-based filtering, content collaborative filtering, recommends items based on their similarity with items that the target user rated. Make sense? Okay. So as everything in the world, nothing is perfect. So there is some pros and some cons. The pros are it's very easy to implement. It's fairly simple. The context, it's context independent compared to other techniques such as content based, which we will be talking about later. It's more or less more accurate, and it's true. It's a little bit more accurate. So. And some will argue that the collaborative filtering system is the most accurate system there is, but apart from the hybrid one, but it depends. So, and the cons are the sparsity. What that means is the percentage of people who rate items is really low. So we will have a small amount of data or small amount of input to work with, okay? And the scalability. So the more users and items there are in the system, the greater the cost of computing will be, and that makes sense as well. So the more users, the more computation we will need, the more the more computing will be, and the more cost it will take. So it will cost us more initially. Ultimately. So, and the biggest problem with this filtering system, this recommending system, is the cold start. So what that means is if we have a new user, we will have basically little to no information about them, and that way we can't compare the user with other users. And same thing with the items. So if we have a new item, that means that there is practically no one saw the item, no one bought the item yet, no one consumed the item yet, and there is no ranking, so the item will not be ranked. This is a cold start for the item as well. So this is where the content-based filtering comes in. So after analyzing the collaborative filtering, which uses the interactions of the user with the different items to make recommendations, we realized that the system have problems, mainly the cold start, which is the biggest problem there is, and the new users, for new users and new items. And we can solve these problems by implementing content-based filtering. The concept of this recommender is born from the idea of using the content of each item for recommending purposes and trying to solve the problems described above. By content, we mean like the variables, the metadata, or the variables of each item, or each product, or so. For example, let's take a book. One of the variables that could be in that book, or the metadata in that book, would be the category that the book belonged to, the collection, the name of the series, the group of people, or the group of age, like age range that that the book is targeting, and so on. Even a description is considered content, like a description of the book. A little text or a paragraph is considered a content as well. So the general idea behind this recommender system is that if a person liked a particular item, he or she will also like an item that is similar to it. So, and likewise, the content-based filtering has some pros and cons as well. One of the pros are, unlike collaborative filtering, if the items have sufficient descriptions, we avoid the new item problem. So just like that, based on the descriptions and the content that we have in the item, we can work with it and find the similarity between that item and other items, and that way we can recommend it, no problem at all. So that solves the cold start problem and the new item problem. The content representations are varied, and they open up the options to use different approaches like text processing techniques, which are ultimately natural language processing techniques, inferences, and other ways. Like we said, the content that could be used is virtually unlimited, like infinite. We can take the variables we need, and each item has different variables, and each company use different descriptions, and so on. So there we have a varied options or varied approaches to choose from. It's very flexible. So it is easy to make more transparent system. So there is not much change we do. So we will apply the same recommendation system and same recommender with different type of items without needing to adjust or change much about the scripts or the recommender itself. And the cons are the content-based recommendation system tend to over specialize. So generally they will recommend items similar to those already consumed, and that way the customer or the user will be in a bubble, like in a bubble of recommendations. You will never leave that bubble, because the recommendation system will be always recommending items that are similar, like the similar. So let's say you like books, the item will always recommend you books, like, so you will stay in a bubble. There is not much expansion in that field, unlike the collaborative filtering system. And the method based on collaborative filtering as well have shown to be more precise when generating recommendations. And so, as we said in the pros of the collaborative filtering, it's more or less more accurate. So yeah. Moving on to the architecture of a content-based recommender system. It contains three principal components: a content analyzer, a profile learner, and filtering component. And by the architecture, we mean like we need to keep in mind that this is a high level architecture of a content based. So what that means, if we are doing a simpler or like much smaller scale recommendation system, we wouldn't find these three components. This is a higher architecture of a big scale recommendation system. So keep that in mind. And yeah, the three principal components are a content analyzer that gives us a classification of the items using some sort of representation, and we will talk about that later. We will touch on the concept and explain it later, what that means. A profile learner that makes a profile that represents each user's preferences, and finally a filtering component that takes all the inputs from profile learner and content analyzer and generates the list of recommendations for each user. So basically how this will work is the content analyzer transforms and prepares the items to be filtered, most likely by applying natural language processing techniques, then calculating their similarity score. Then the profile learner take the user's input, by user's input we mean the item that the user is viewing, buying, clicking, etc. So this will be the user input. Then the filtering component, which is our filtering system, ultimately take the input from the content analyzer and the profile learner, compare similarity of the item viewed with other items, and it will recommend the items that has the highest similarity score. So by that we mean, and I'm sorry, if the user clicks on the recommendations that we provided, or one of the recommendations we provided, we get, as we can see in the graph or in the picture, we get also a feedback that goes into the profile learner. And with that we will of course take the feedback into consideration for future recommendations. So how do we prepare, like we talked about preparing and representing the items variables. So how do we do that to ultimately do a similarity score analysis? Well, the content of an item, like we said, is can vary and is a very abstract thing and gives us a lot of options. We could use a lot of different variables. For example, if the item is a book, as we explained before, we could consider the author, the genre, the text of the book itself, the description of the book, and the list goes on. So once we know, we made our minds which content or variables we will consider, and this will most probably take place in the EDA phase, exploratory data analysis phase, where we will get familiar with the data, with the data set, with everything, and then decide based on what the insights we have and the information we have on the data. So once we decide which variables we will be using, we need to transform all this data into a vector, like vector space model. This is like, which is a mathematical representation of a text documents, basically NLP, transforming letters to numbers. This is the general concept. So generally, we do this with a bag of words. This will represent documents, ignoring the order of the words. And in this model, each document looks like a bag containing some words, hence the name, the bag of words. And there are two main implementation of a bag of words. The first one will be TF-IDF, like we are seeing here in the table. in the example we provided, and a count vectorizer. So starting with the TF-IDF, what is it? So it's basically a relative. It's basically how important the word to the document. The importance, like calculating the importance of the word in that document or in that item. And this is how it goes. It is the relative frequency, which is the TF part, the first part. It's the relative frequency of a word in a document or an item. Then we have the inverse document frequency. The IDF part is the relative count of document that contains the word. So they're not the same. They are different. And the overall importance of each word to the documents itself is equal to TF multiplied by IDF. So we will multiply the two results, the two numbers. This will give us a matrix like we are seeing here, where each column represents a word and each row represents an item. This is done to reduce the importance of words that occur frequently and therefore their significance in computing the final similarity score. So basically manipulating and adjusting the weight of each word in each document or each item, if you say. And then we have count vectorizer, which is much simpler than the TF-IDF. It's basically used to convert text documents to a vector of word counts. It does the same thing as TF-IDF, but without calculating the importance of words. So we just get a count number of the word, like how many times that word appeared in each item. And that's it. And now we will move on to a real project example, the project that we did. And in this part, we will see a book recommendation system we created for a client. We can't mention the client's name nor show the real data for obvious reasons, for privacy and security reasons. And what we did is we used hybrid filtering that combined the results of collaborative and the content-based filtering. But in this representation, but this will serve as an example of only the content-based filtering system. We will only show the content-based system, and finally providing a step-by-step Python script explanation, like we can see here. So in this recommendation system, the content of the book, like we mentioned before, would be, or the variables we are using will be the range, the age range, the category, the collection, the series, the languages of the books, and the keywords. Like let's think about the keywords as tags. We're fairly similar. And all of this content, these variables, is used to find the similarity with of one book with other books. So we will be using this variables, this metadata. And how that will work, we calculate cosine similarity scores for all books based on their metadata we are providing, and recommend books based on that similarity score. So books with the highest similarity score are then recommended, okay? And then we create our metadata soup, basically the bag of words we talked about, which is a string containing all the metadata we want to send to our vectorizer. The vectorizer will be either a TF-IDF model or a count vectorizer. So we can see here the soup, or the bag of words we created. We named it combined features. This is the new variable we are creating, and it will contain all the variables or metadata, the content of the books we have. We will put it into one variable. Okay, and then create the count matrix by introducing the combined features we just created into the count vectorizer. The vectorizer we will be using is a count vectorizer as we can see here, and we calculate the similarity score using scikit-learn built-in feature named cosine similarity. So this feature here. So basically, when you import the scikit-learn, the library, you import this feature as well, cosine similarity, and that way you provide it with the two matrices, which is the same matrix twice, and the matrix is will contain the number of words for each item. Like the count matrix will have columns as the words, and rows as items, and in the cells we will have the number of words, like how many times that word appeared in each item. Okay, so it will be matrix. Let's say, for example, we have 400 400 books, for example. We introduce that same matrix with 400 item and God knows how many words. We introduce it twice. Why? Because we take the first matrix and the second matrix. We take the first item, which is the first book, from these 400 books, and compare it, like with the first item in the other matrix, the second item, the third item, the fourth or the fifth, and so on. And we compare it with 400 items. When we finish the first item from the first matrix, we jump to the second item and we compare it to 400 item from the second matrix, and so on. So we will compare the 400 from the matrix, the first matrix, with the 400 with the second matrix. And this is how we get the similarity score of every item with other every item. So this is how we compare and calculate the similarity score between items. So here, and then we are now in a good position to define, after we created the bag of words, the feature, the combined feature, after we introduced it to a count vectorizer, after we create the matrix with all the count number and the count and calculations of the appearances of the words, we created the matrix, and then we introduced that same matrix twice into the cosine similarity feature that is built in the scikit-learn model, and calculating the similarity score. So now we have the similarity score of each item we have, and we are now in a good position to define our recommendation system. So these are the steps that the function follows. The steps are get the index of the book given its title, so we will specify the index of the book we want to compare or to get the recommendations to, and then get the list of cosine similarity scores for that particular book with all books converted to a list of tuples where the first element is its position and the second element is the similarity score. So then after we get the index of the book we want to find recommendations to. Then we call the other items with that have a cosine similarity, with all their cosine similarity with that book, and we put it into a tuple. Okay, and then we sort that list of tuples mentioned above based on similarity scores. So we sorted from highest to lowest. After we sort it, we get only the top 20. So we will eliminate the rest, which will be like 380 items. We'll eliminate 380 items, and we will keep 20. And by the way, we ignore the first item that has the highest similarity score because it will be the same item itself, basically the same book itself. So the book most similar to a particular book is the book itself. I hope that makes sense. It's a bit confusing at the start, but if you think about it, it makes sense. And then after we keep the 20 recommendations, we return the title corresponding to the index of the superior elements. So this is practically what the function does. These are the steps, the 5 steps of the function. And with that function, we get a list of 20 recommendations for each item. After we get the recommendations we needed, then we create a data set with the recommendations we get for further exploration and for further insights or further utilizations. Okay. And finally, the pipeline. So for the final step of the project, we implemented a pipeline in Microsoft Azure Machine Learning portal, using the designer to essentially contain the steps we talked about earlier. The main goal here was to automate many of the manual steps involved in transforming and optimizing the data loads using the Python scripts we created earlier. The script that we showed earlier is only but a fraction of the scripts that we created, but that was the part of the content-based recommendation. And this pipeline, for example, contains or includes a way of loading the raw data, cleaning it, transforming it, preparing it before finally giving us the book recommendations we want, and ultimately inserting it into reporting tables like the output table. So here we can see the input data. These are the data sets we have. This block here contains a script for data pre-processing, data preparation, and data cleaning. And then from this block we move to two parts, the right one and the left one. So on the left one we have a collaborative filtering system, which is provided and supported by the designer of Azure Machine Learning portal itself. So it provided us with a built-in model of collaborative filtering. And then here on the right we have the recommendation, the content-based recommendation filtering we were just talking about. So these two blocks will contain the scripts we just saw. Okay, the same script, nothing complicated. If we open one of these blocks, we will see the same code as this, with the same function, the same transformation, and the same way we created the matrices, and the same way we calculated the similarity scores. And finally, so here we get the results of the content based, as we saw here previously. And here are the results of the, the collaborative filtering recommendation. So we will combine these two results from these two different filtering systems into one. And this point here is where we create the hybrid filtering system. And this hybrid filtering system, then we merge recommendation with other data that the client provided us with. We do some data some data engineering, some data transformations, some more exploration, and to get more insights about the results, whether the results make sense or no, whether we can improve them. We did find some things to be improved. For example, here we found out that the recommendation systems is recommending books like correctly with higher precision or high accuracy, and the client seemed to be fairly satisfied with the results, but with one exception, with one problem: languages. So, for example, let's say we have a client that sells books only in English, okay? But here in the the recommendation system is recommending books to that client that is in Spanish. So the client, so that's an irrelevant recommendation. This is mainly the problem we encountered. So what we did, we created a filter to filter more the data and leave out the wrong or not suitable, not so relevant recommendations, and only recommend the books that we feel like they are accurate or they are relevant. And here we did some limitation. We don't want to bombard the clients with a lot of options. So this is, after all, the reason we are creating the recommendation system in the first place. So after merging the two systems, we get more than 20 recommendations. What we did here is filtering these recommendations and filtering more the recommendations we get and downing it into 20 recommendations at the end. Here we did some more enrichments and more data manipulation to get more rich data sets and more rich results, to get to be able to see more insights, more important insights. And finally here we have the export data, which will be the big output at the end. And hopefully that was helpful. Hopefully we learned something new today, and hopefully that wasn't too boring. Here I will leave these links that helped me at the start to learn more about these recommendation systems, and helped me a lot with the project we did with the clients, and helped me as well creating this and preparing this presentation to you. So I will leave this links here. And I would like to thank again the sponsors for making this event happen, and for this great and amazing experience. And thank you so much.